Welcome, everyone. Today, we're diving into a document that's not just a piece of science history, it's the birth certificate for entire fields of modern medicine. We're talking about Marie Curie's 1904 doctoral thesis, Recherches sur les substances radioactives. This wasn't just an academic paper, it was a revolutionary blueprint that laid the groundwork for everything from nuclear medicine to radiation oncology. And just so you know, all the sources we're discussing today, including Curie's thesis, are linked in the description below.
So let's bring this right into your world. Think about the last time you ordered a PET-CT. You're looking for that bright spot of metabolic activity. But what fundamental property of matter, first measured in a leaky shed in Paris, is actually allowing you to see that?
Or how about this? When you're planning radiation therapy for a patient, how is that connected to the almost impossibly difficult task of separating a brand new element from literally tons of rock ore? Well, the answers to both of those questions start right here, inside this thesis.
Okay, so our story begins with a real puzzle. After Henri Becquerel's discovery that uranium salts gave off these strange, invisible rays, Marie Curie decided this was something worth digging into. She set out to systematically measure this new phenomenon in every element she could find, and that's when she stumbled upon a major anomaly, a real head-scratcher in the raw uranium ore itself.
Now check out this data, pulled right from her work. Using an electrometer her husband Pierre helped perfect, she measured the electrical current these rays produced. Pure uranium metal clocked in at a radioactivity of 2.3. But then look at pitchblende, the mineral that uranium comes from. It's at 8.3, nearly 4 times higher. Chalcolite was more than double. This made no sense. How could the raw, crude ore be more radioactive than the pure active element extracted from it? There was only one possible answer. Something else had to be in that ore, something new and incredibly powerful.
This paradox forced her to invent a completely new way of doing science. Forget looking for color changes in a test tube. Her guide was the invisible radiation itself. You could call it chemistry by glow, where her electrometer was like a new set of eyes, letting her follow the trail of this mysterious hidden substance. And her method was just brilliant. It was so simple, yet so rigorous. Step 1, she'd take a chunk of pitchblende and use standard chemistry to break it down into different parts, or fractions. Step 2, she would meticulously measure the radioactivity of every single one of those fractions. And step 3, the crucial part, she'd throw away the boring, less active stuff and focus all her energy on the hottest sample. Then she'd just repeat the process, again and again. For the first time, radioactivity wasn't just a curiosity, it was a tool for discovery.
And boy, did this method pay off. It didn't lead to one discovery, it led to 2. First, she found a highly radioactive substance that tagged along with the element bismuth in her separations. She named it polonium, a tribute to her native Poland. Then she found another one, this time following the chemistry of barium. This second one was so unbelievably radioactive, they called it radium, after the Latin word for ray.
But detecting the signature of new elements is one thing. To prove to a skeptical scientific world that they were real, she had to isolate one of them. She had to hold a pure sample in her hand. And this is where the work transformed from careful lab science into a Herculean, almost industrial effort.
I really want you to just let this number sink in. To get just a few decigrams of radium chloride, that's a tiny fraction of a gram, the Curies processed literal tons of pitchblende waste. They were in a drafty, cold shed, stirring these huge cauldrons of boiling hazardous chemicals. It was like sifting through a mountain of sand to find a few grains of atomic gold.
And this right here, this is the payoff for all of that brutal work. To separate the radium from its chemical doppelganger, barium, Curie used a slow, painstaking process called fractional crystallization. And with each grueling step of purification, she measured the atomic weight of the sample. Look at the numbers. The starting mix was near 140. With more purification, it climbed to 145, then 173, until finally it settled at 225. This was the smoking gun. Barium's atomic weight is 137. This was something completely new.
Okay, so now that they finally had pure radium, the scientific community could really dig in and figure out what these incredible emissions were all about. By shooting the rays through a magnetic field, researchers quickly realized it wasn't just one type of radiation. It was a complex cocktail of at least 3 very different things.
And this is where that direct line to your daily practice becomes crystal clear. They found low-penetration, positively charged alpha particles. That's the exact principle behind the targeted, short-range brachytherapy seeds we use today. They found median penetration, negatively charged beta particles. Well, that's the foundation for systemic radiopharmaceuticals like iodine-131. And then they found the heavy hitter, highly penetrating, uncharged gamma rays, the very same radiation hitting tumors in our linear accelerators every single day.
So let's put it all together. Let's distill this amazing history down to its high-value clinical legacy. How does the work from that 1904 thesis move from a lab in Paris directly into your clinic?
It comes down to 3 key principles you use every day. First, the principle of radioguidance. Every time you see a tumor light up on a PET scan, you're using the direct descendant of Curie's method of following the glow to trace a biological pathway. Second, the concept of differential energy. The entire field of radiation oncology, our ability to treat deep tumors while sparing the skin or to use different particles for different jobs, it's all built on the discovery of alpha, beta, and gamma rays. And third, the dawn of dosimetry. That moment, Curie decided to quantify radiation with her electrometer. That was the birth of dosimetry, the science of measuring radiation dose that is absolutely critical for safe and effective treatment.
So here it is. Here's your conversation starter. A great way to remember the core lesson here. From pitch blend to PET scan, follow the glow. It all started with following that invisible signal.
So to wrap this all up, Curie's thesis was so much more than an academic paper. It really was the birth certificate of a new age in science and medicine. So here's the challenge. The next time you're looking at a nuclear scan or planning a radiation field, take a second to remember the principles of activity and separation that were born in that Parisian lab. Challenge yourself to see the foundational science behind the incredible technology you use every single day.
Disclaimer and bibliography in the description.